Imagine sitting in a really busy coffee shop. You're setting up for a morning of work, and you carefully type out your, 20-character, highly complex password to log into your company's network.
Right, and you feel totally secure doing it.
Exactly. You think you are perfectly safe because, well, your company spends millions of dollars on state-of-the-art firewalls and encryption, but the person sipping a latte at the table right behind you just bypassed all of that million-dollar security.
Just by watching.
Yeah. Simply by watching the movement of your fingers on the keyboard.
It is really the ultimate irony of system security. I mean, we build these massive, complex digital fortresses, but we often forget that the front door is operated by human beings out in the real world.
Okay, let's unpack this.
Yeah.
Because today, our mission is to look at system architecture from the perspective of the attacker.
Right.
We're diving into the mechanisms of system hacking, specifically how attackers crack passwords, exploit authentication, and basically slip past the digital bouncers guarding your data.
We're pulling all of this from the official Certified Ethical Hacker Curriculum. It's the CEH v13 material.
Yeah, and we're looking at the actual playbooks used to compromise systems. But before we get into how an attacker breaks in, we really need to understand how your computer is trying to keep them out.
And that starts with understanding where your secrets actually live. So in the Windows operating system, that digital vault is called the SAM database, which stands for the Security Accounts Manager.
Okay, the SAM.
Yeah. And the absolute foundational rule of this architecture is that your password, no matter what it is never actually saved in clear text.
So it's not just sitting there in a document.
Exactly. If an attacker manages to rip open that SAM database, they will never see the word password123.
They see a hash, right?
Yeah.
Which, to use an analogy, is kind of like turning a cow into a hamburger.
I love that analogy.
Right. You put your password in, the computer runs it through a complex mathematical algorithm, and it spits out this scrabbled string of characters.
Yeah.
But you can't reverse the process to get the cow back.
That is a highly visceral, but, entirely accurate way to look at it. The math only goes one way.
So the attacker isn't trying to unhamburger the meat.
No. The system doesn't actually know your password. When you log in tomorrow, Windows just takes whatever you type, turns it into a hamburger, and compares it to the hamburger it has saved in the SAM database. If the hashes match, you get access.
Well, knowing that the SAM file holds all these hashes, Microsoft obviously doesn't just, leave it sitting out in the open.
Oh, they guard it fiercely. I mean, while Windows is running, there is an exclusive kernel-level lock on the SAM database on your hard drive.
So I can't just drag and drop it.
No way. You cannot simply copy it and paste it to a thumb drive. That lock literally does not release unless the entire operating system shuts down or, throws a fatal error.
Oh.
And beyond that, Windows uses a function called syswski to add another layer of encryption to those hashes while they sit on the physical disk.
But attackers still target it. And looking at the materials, it seems like Windows has a bit of a ghost haunting its security architecture.
Oh, definitely.
Like older systems use something called LM hashes, and newer ones use NTLM. What makes the older ones such a liability?
What's fascinating here is how legacy systems just continue to haunt modern security. It really comes down to the architectural limitations of the 1990s.
Okay, the 90s.
Yeah. The older LM hash protocol is notoriously weak because, it maxes out at 14 characters. But the fatal flaw is how it actually processes those characters.
What does it do?
The system takes your password, immediately converts all the letters to uppercase, and then chopped it into 2 separate 7-character chunks before hashing them.
Wait, seriously? So if my password is 14 characters long, the attacker doesn't have to crack one massive 14-character math problem.
No, they don't.
They just have to crack 2 tiny 7-character problems.
Precisely. It makes the math exponentially easier to solve. Now, modern Windows versions, they use NTLM and they disable those old LM hashes by default.
Right, which makes sense.
But here is where legacy compatibility haunts us. To ensure that an old network printer from, say, 1998 or a legacy piece of software can still authenticate, the modern SAM file still has to manage that old LM architecture.
Oh, man. So it's still there.
It is. If you set a password longer than 14 characters today, Windows just stores a blank sort of dummy value in that old LM hash slot. It is a constant tug of war between keeping systems locked down and making sure businesses can still run their old hardware.
It's like putting a modern retinal scanner on a bank vault, but leaving a flimsy screen door right next to it, just in case a customer from the 90s shows up.
Yeah, it's exactly what it's like.
Which brings us right back to the coffee shop scenario we started with. If the digital locks, these hashes and kernel-level file system locks, are so complicated, why try to pick them at all?
Well, you don't. You take the path of least resistance. This is the whole domain of non-electronic attacks.
Here's where it gets really interesting.
So far.
Because companies spend a literal fortune on firewalls, but their biggest vulnerability is just human nature.
Absolutely.
The curriculum points out that a helpful employee, or a poorly shredded piece of paper, is often the easiest way in.
Dumpster diving is the classic example here. I mean, it sounds like a trope from an old hacker movie from the 80s, but the reality is that support staff and everyday employees constantly throw away sensitive physical media.
Like what?
We are talking about sticky notes with administrative passwords, outdated network topology reports, system manuals, or even hardware receipts.
Wow.
Yeah, all an attacker needs is a pair of gloves, a dark evening, and a willingness to dig through the trash outside the office.
Bypassing millions of dollars of cryptography with the garbage bag. That's wild. And then there is shoulder surfing, like our coffee shop example, just hovering near a target.
It is remarkably prevalent. Think about watching someone punch a 4-digit PIN into a grocery store checkout terminal.
Right?
A 4-digit PIN takes less than a second to memorize. If you apply that same tactic to an employee working on a laptop on a crowded airplane or logging into a portal at a cafe.
The attacker just watches the keystrokes.
Exactly. And if they can't see your screen, they might just call you and ask for the password. Social engineering.
Just flat out ask for it.
Human beings generally want to assist each other, you know? We are wired for cooperation. Social engineers exploit that psychological trait.
They use our helpfulness against us.
Right. They might spoof a phone number to make it look like they're calling from the internal IT department. They tell the user, hey, we are detecting a critical error on your account. I need you to verify your password so I can clear it and save your work.
And the user falls for it.
Because the user genuinely believes they are solving a problem, but they are actually handing over the keys to the kingdom.
So if we relate this to you, the listener, how do you even fix that? I mean, you can't download a software patch for human empathy.
No, you can't. The defense here is entirely cultural. It requires active, continuous education.
Training.
Yes, training the humans involved to recognize the immense value of the mundane information they handle every day and teaching them to verify identities before being helpful.
Okay, but let's assume the humans are perfectly trained. The trash is burned, everyone has privacy screens on their laptops, and literally nobody talks to strangers on the phone.
A perfect world.
Right.
Right.
The attacker is forced to go back to the digital front door. But they aren't typing passwords by hand, are they?
No, they move to active, online, automated guessing. The baseline here is a dictionary attack.
Okay.
The attacker takes a massive text file containing millions of commonly used passwords. The most infamous one is actually called rockyou.txt-, and they load it into a cracking application.
Okay, trying a massive list of plain words makes sense. But what if my company forces me to put a number and a symbol at the end of my password? Like, a basic dictionary wouldn't catch password 123.
And that is exactly why attackers evolved to use rule-based or mask attacks. They know about those corporate password policies.
So they adjust for it.
Right. They tell the cracking tool, take every single word in this dictionary and automatically append 123 to the end of it before you guess. Or they use toggle case attacks, forcing the tool to try every single combination of uppercase and lowercase letters for every single word.
What about combining words?
Those are combinator attacks, where the tool merges two separate dictionaries, but the evolution of that is something called a Prince attack.
Prince.
Yeah, it stands for Probability Infinite Chained Elements. It takes short, common building blocks from a dictionary and chains them together to build long, complex-looking phrases.
Interesting.
So pass and word become password, but it scales up to create entirely unique, multi-word passphrases that look incredibly secure, but are actually just made of basic parts.
Wait, hold on. Chaining infinite words together seems like it would take a ridiculous amount of time. And more importantly, if a system locks you out after 3 failed attempts, how does an attacker sit there and guess thousands of chained passwords online without getting blocked?
That exact hurdle led to a brilliant shift in tactics known as password spraying.
Spraying.
Yeah. Instead of acting like a traditional brute force attack, which, hammers thousands of different passwords against one single user account until the system locks it down, password spraying flips the methodology completely sideways.
How so?
The attacker uses a tool like THC Hydra. They pick just one highly probable password, let's say winter 2024.
Very common.
Very. Then they try that single password against every single user account across the entire company directory.
Oh.
Because they only tried one incorrect guess per person, nobody hits that 3-strike lockout threshold. The attacker stays completely silent, relying on the statistical probability that out of 500 employees, at least one of them used that exact weak password.
Wow. They completely sidestepped the alarm system.
Totally.
But even spraying leaves a trace in the network logs. There is a whole section in the curriculum about methods that are even stealthier, moving from guessing the password to just quietly intercepting it on the local network.
This relies on understanding how Windows handles local network traffic, specifically older protocols called LMNR and NBTNS.
Okay, LLMNR. Link. Local Multicast Name Resolution. So put this in context for me. What happens if I am trying to connect to a shared folder in my office called Data Server, but my finger slips and I mistype it as, like, Data Serve?
Well, your computer first asks the official corporate DNS server to connect you. The DNS server checks its records and replies, I have no idea what DataServe is.
Which makes sense.
Now, logically, your computer should just show you an error message and stop. But because of those older protocols we mentioned, it doesn't.
It keeps going.
Instead, your computer blindly shouts out to every other machine on the local network asking, hey, does anyone here know how to connect to DataServe?
Why would it do that? Why would Windows be designed to blindly shout into the void?
This raises an important question, right? It goes back to the convenience of 1990s networking.
The 90s again?
Always. Microsoft wanted small offices without dedicated IT staff or complex DNS servers to be able to just plug two computers into a switch and have them immediately find each other. It was designed for plug-and-play convenience.
But the convenience feature of yesterday is the vulnerability of today. Because if an attacker is sitting on that same local network, they can use a tool called Responder to listen for that shout.
Exactly. Responder hears your computer asking for DataServer and immediately replies, yep, that's me. I am DataServer. Send me your authentication credentials so we can connect.
And my computer just blindly hands it over.
It automatically sends over your NTLM hash. The attacker captures it, and they now have the scrambled math of your password.
That is terrifying. But then the curriculum mentions something called an NTLM relay attack, where the attacker doesn't even bother trying to decrypt that hash.
The relay attack is devastatingly efficient. They use a tool called NTLM Relax.
This sounds exactly like a fake valet scam.
Oh, how so?
Like, imagine pulling up to a fancy restaurant. You hand your keys to a guy wearing a vest. He takes your keys, and he goes and parks your car. To you, everything seems totally normal.
Right.
But while he's doing it, he makes a copy of your key. He acts as the invisible middleman between you and the actual parking garage.
That analogy is spot on. In a relay attack, the attacker intercepts your authentication request, but then immediately passes that exact valid request to the real server they actually want to break into.
Wow.
The real server looks at the hash, sees that it came from your legitimate computer, and grants access. The attacker rides that granted access to do immense damage, like dumping the entire SAM database from a domain controller.
Okay, but we've been talking a lot about NTLM hashes.
Yeah.
Earlier in the materials, it mentions Kerberos as the modern gold standard for Windows authentication.
Yes, Kerberos is much more robust.
Because Kerberos doesn't use those easily intercepted hashes, right? It uses encrypted tickets. So if a network upgrades to Kerberos, this interception stuff stops working.
Well, attackers are incredibly adaptable. If the architecture shifts to tickets, the attackers shift to hunting tickets.
Ah.
Kerberos relies on a trusted third party called the Key Distribution Center, which issues a ticket granting ticket, or TGT, to prove your identity.
Okay, think of a TGT like the wristband you get at a multi-day music festival.
Okay, I like that.
You show your ID once at the main gate, they give you the wristband, and from then on, you just flash the wristband to get into the different tents. You don't have to keep pulling out your driver's license.
Exactly. And just like our wristband, those digital tickets have to be stored somewhere while you are using them. In Windows, they are cached in the system's temporary memory, the RAM.
In RAM.
Specifically, inside a process called lsas.exe, the Local Security Authority Subsystem Service. Windows keeps them in memory so that every time you open an email or access a shared drive, you don't have to manually type your password again.
So what does this all mean? If it's sitting in memory, it can be scraped.
Yes. Using a notorious post-exploitation tool called Mimikatz, If an attacker gains even basic access to your machine, they run Mimikatz to peer directly into that ALSAS process.
Unbelievable.
Mimikatz can pull out active Kerberos tickets right out of your computer's RAM.
So if you, the listener, step away from your laptop to grab a coffee, your digital wristband is just sitting there in memory. The attacker scrapes it and performs a pass-the-ticket attack.
Right?
They just present your stolen wristband to the server, and the server lets them right in. They bypass the password completely.
They completely sidestep the authentication phase. And there are even more aggressive ways to attack Kerberos, like Kerber roasting.
Kerber roasting.
Yeah, this targets service accounts. Any regular user on a network can request a ticket to access a specific service, like a database. The server sends you that ticket, and part of that ticket is encrypted using the password hash of that service account.
So the attacker just acts like a normal employee, asks for a ticket to the database, and then quietly takes that encrypted ticket offline to crack the map on their own computer.
That is the core mechanism. And because service accounts often have incredibly high administrative privileges, and their passwords are almost never changed, cracking one gives the attacker massive control over the network.
The curriculum also details something called ASREP roasting. How does that differ from Kerber roasting?
ASREP roasting is frightening because it doesn't even require the attacker to be authenticated on the network.
Wait, really?
Yeah, it targets user accounts that have a specific vulnerability. A setting called Do Not Require Kerberos Pre-Authentication has been turned on.
Why would an IT administrator ever check a box that turns off pre-authentication? That sounds like asking for trouble.
Again, it comes down to legacy requirements. Some older applications, custom software, or specialized hardware simply do not know how to perform the modern Kerberos handshake.
So administrators check that box to force the system to accommodate them.
Exactly. But when that box is checked, an attacker can simply send a blind request to the network saying, "Give me a ticket granting ticket for this user."
And the server just gives.
The server just hands it over, fully encrypted with that user's password hash. The attacker saves it to a thumb drive, walks away, and begins cracking it.
Which brings us to the final crucial phase. You asked earlier about how an attacker has the time to compute all these massive chains of words in a Prince attack.
Right.
Whether they stole an NTLM hash with Responder or grabbed a Kerberos ticket through ASREP roasting, they now have an encrypted file sitting on their own computer. How do they actually break that math open?
Well, once the data is taken offline, the attacker has a massive advantage. They don't have to worry about triggering network alarms or getting locked out.
Because they're offline.
Exactly. The only two variables left are time and computational power, and they have incredibly sophisticated ways to conquer both. To defeat time, they use rainbow tables.
The curriculum mentions a tool called Zircon for this. What makes a rainbow table faster than just guessing?
It is based on a cryptanalytic concept called a time-memory trade-off. Calculating the complex math of a hash on the fly takes processing time. So instead of doing the math in real time, attackers use massive pre-computed tables.
Like a cheat sheet.
A rainbow table is essentially a giant digital phone book. It already contains millions of common passwords and their perfectly calculated hash equivalents.
So instead of doing the math, they just scan the phone book. If they see the stolen hash printed on the page, they just look across the road to see what password created it. It's instant.
It reduces weeks of processing time to mere milliseconds. But if the password isn't in the rainbow table, they have to rely on raw computational power. And this is where they use distributed network attacks or DNA.
This part blew my mind. DNA tools like Elcomsoft or PRTK. Explain how this works.
If we connect this to the bigger picture, a DNA attack hijacks the unused processing power of multiple machines to work on the math problem collectively.
So it spreads the work out.
Yeah. An attacker manages to install a small, silent DNA client across hundreds of employee computers in a target network. The manager program takes the incredibly complex hash, chops the mathematical workload into thousands of tiny pieces, and hands them out to all the idle computers in the office.
Wait. So the attacker is literally using a company's own processors, like an entire office of idle computers against themselves, to crack a single, highly privileged password.
Yes, they turn your own infrastructure into a weapon against your encryption.
That is insane.
But standard computer processors, CPUs, are designed to handle tasks sequentially. If an attacker really wants to process millions of math problems simultaneously, a standard processor isn't going to cut it. They need something designed specifically for massive parallel processing. They need GPUs.
The graphics cards.
Right. Graphics processing units are built to render millions of individual pixels on your screen all at the exact same time.
So they do lots of little things fast.
Exactly. That unique parallel architecture makes them devastatingly efficient at performing the repetitive mathematical calculations required for brute-forcing complex hashes.
But the curriculum highlights a GPU attack that doesn't even bother with the math. It involves tricking a user into downloading malware that targets the cross-platform APIs, like OpenGL.
This is the ultimate subversion of the architecture. The malware hooks directly into the OpenGL API, which is the bridge to your graphics driver.
What does that do?
By doing this, the attacker isn't trying to crack a hash. They are secretly tracking your activities as they are rendered on the screen. They can sniff your keystrokes visually.
Visually.
Before your password is even turned into a hash, before it is ever sent over the network, the attacker has simply watched you type it by hijacking your graphics card.
Unbelievable. We have covered an incredible amount of ground today. We started in the physical world, looking at how attackers bypass encryption entirely by digging through dumpsters or, watching you type at a coffee shop.
The low-tech stuff.
Right. And then we explored the quiet interceptions, where a single typo on a local network causes your computer to blindly hand over its hash to a fake valet.
The responder attacks.
Exactly. We looked at how they rip your digital VIP wristbands straight out of your computer's memory. And finally, we saw how they use pre-printed rainbow tables and distributed GPU networks to chew through encryption offline.
What this journey really illustrates is that system security is never a single impenetrable wall. It is an intricate, ongoing process of managing risk at every single layer, from how humans behave in public, to how memory handles temporary data, to how network protocols prioritize convenience over verification.
Which leaves me with a final lingering thought based on everything we've unpacked today. If our hashes can be pulled right out of RAM, and if our network requests can be intercepted by fake servers just listening in the dark, and if offline computing power is scaling so fast that it can chew through even the most robust mathematical encryption, are passwords themselves fundamentally obsolete? I mean, if even the strongest, most complex 20-character password can be entirely sidestepped by stealing a Kerberos ticket that was left sitting in memory, shouldn't we be looking toward a completely passwordless future?
It's a great question.
And if we do finally kill the password, what new terrifying vulnerabilities will that architecture create?
That is the perpetual cycle of system architecture. Every new lock inevitably invites the creation of a new kind of lockpick.
Well, on that cheery note, thank you so much for joining us for this deep dive. Stay curious, keep an eye on your local network traffic, and whatever you do, keep questioning your assumptions about security. We'll catch you next time.